Now we're turning to step 4, fitting cycles using random cycles coefficients. That is, coefficients that vary across the individuals. So that's the Cosinor model with random beta 1 and beta 2. And just to remind you where we are in the big picture, let's go back to slide 6. And we are now in step 4 down here. We've gone through finding the cycles, fitting the cycles, finding deviations from the cycles, and now we're to fitting cycles with random cycles coefficients. And the ending step is explaining those random cycles. So back to slide 26. We are focusing on two kinds of models here. We know that we have many Cosinor model versions. We have both two-level RDSEM and cross-classified RDSEM and DSEM, and within each we have fixed and random coefficient versions. Now we're focusing on the random cycles coefficient versions. So two-level RDSEM, coefficient variation on the between level. Of course, the Cosinor covariates are on the within level, and that's what gives rise to the residual DSEM notation. Now, this two-level analysis is suitable if you have a small residual variance on the between time level from the derived from the step 2a analysis. And that may be a reasonable approximation in this case. However, there is also the cross-classified RDSEM, which we took a look at in the 3b run, where we used a model with cycles on the within level, and which would then allow coefficients variation on the between ID level, just like on the between level in two-level RDSEM. But it's much more time-consuming than two-level analysis. So we're going to focus on the two-level RDSEM, but it is possible in principle to do this step 4 using cross-classified RDSEM as well. On slide 27 then, I point out that what we want to do when we have established random cycles coefficients is to try to explain that variation across individuals by covariates, background characteristics for the individuals, time invariant covariates. And that interpretation of the cycles is much more clearly done by translating the beta coefficients to amplitude and phase. It's true that beta 1 and beta 2 effects can be understood in terms of emphasizing the sine or the cosine coefficient and its impact on the cycles. We saw that in an early plot, but it gets cumbersome to work in that metric. It's better to focus on the amplitude and phase, the vertical variation and the horizontal variation. And that can be done very efficiently in a two-step analysis. In step 5a, the first step, we do a two-level RDSEM with between-level covariates, where we do multiple imputation at the end of the run for the random beta cycles coefficients using a save data command. We're going to take a look at that. For example, as it says here, you can ask for 200 plausible values. That's the 200 value that we've seen before. 200 draws from the posterior distribution of the two beta coefficients for each person. So therefore, there are 200 data sets, and each of the data sets has n rows, the number of rows that you have in the original data set, or at least in the data set that is analyzed by t-interval. And the columns are the two random coefficients and the between level covariates. That is, the between level components of the model. Step 1.5b then is a single level analysis using type equals imputation. That's the analysis type. and actually it's the data type, and translation in the defined command of the beta coefficient into amplitude and phase. So for instance, we see the amplitude for individual I is that formula we saw earlier, square root of the sum of the squares of the beta coefficients. And once we've translated them into define, we can then regress the amplitude and the phase on the covariates, the between level covariates, in a single level analysis. Doesn't even need base. On slide 28, I talk about step 5 in terms of cycles for factors behind the PA items. So we're going to do step 5A and 5B for factors. And what do I mean by that? Well, we have 6 PA items: relaxed, satisfied, confident, happy, energetic, and excited. And what we've done so far is to use a PA variable that is a sum of those 6 items, 7 category items. But a multi-level factor analysis, a 2-level factor analysis, actually show that there are 2 factors. And they can be characterized this way. You have, for the first factor, you have strong loadings for the relaxed, satisfied, and confident items. And for the second factor, you have high loadings for being happy, energetic, and excited, with a cross-loading for the happy items loading on both factors. And that corresponds to how the researchers here of this study characterize the items. They characterize these first 3 items as low arousal items and the last 3 as high arousal items. So there's a little bit of a misclassification with respect to happy. It loads on both factors. But you have a clear separation between the factors. This is on the person level, variation across people, and this is on the within level. You have the same structure, just a little bit lower loadings. And the 2 solutions also differ in terms of the factor correlation. Factor correlation for between person factor analysis is 0.83, and for within it's 0.65. And you see a similar situation in two-level factor analysis in general, where between level factors are more highly correlated than within level factors. So the modeling that we're going to do is looking at cycles for these factors, and we're looking at them for the within level factors, the less highly correlated factors. That's where the cycles are going to be specified, not for the between level. Slide 29 shows the result of the factor analytic cycles modeling. So at the top we show the curves for the low arousal factor, and at the bottom the high arousal factor. So we have the same 7 weekdays, and what we're showing here is red being the cycles curves, and the blue being the factor scores that we get at each time point. So these are factor scores that are estimated due to the by statements. So actually a factor measured by the PA items. So here we get those blue estimates, and again we see this deviation on a Saturday, perhaps on Sunday as well, where the cycles modeling underestimates the PA level, the low arousal PA level. We also notice that the low arousal factor variation is a little bit higher, has a higher amplitude than the high arousal factors. They're on the same y-axis scale. Now, the high arousal factors, they seem to follow the cycles. Cycles seem to follow the data, or the factor scores rather, quite well here, and you see that reflected in the R-square values being 0.48 for the low arousal factor and 0.59 for the high arousal factor. So we have a more pronounced cyclic behavior for the high arousal factor. And in the epilogue, we're going to see a potential explanation of that phenomenon. Now, how is this done? How do we get here? Well, let's take a look at slide 30, which looks quite complex at first glance, but let's go through it slowly. So we're in the setting of two-leveled DSEM with random cycles coefficients and factors related to time invariant covariates. So now we're going to bring in the covariates, and we have then, if we focus on the upper right hand side here, we see the 6 PA items. They're observed variables, and they're measuring two factors, F1 and F2, low arousal and high arousal, and with PA4 being the happy item, which is influenced by both factors. And on that within level, we have the cycles covariates X1 and X2. They are within they're time varying covariates, we can call them, so within covariates. And they influence the two factors differently. So factor 1 is influenced by this arrow and that arrow, and factor 2 by this and that. And we see that all 4 arrows have filled dots on them, so they are random coefficients varying across individuals. And therefore, on the between level, those random coefficients become latent variables, open circles, which we want to relate to background variables. In this case, gender, STQ, a measure of childhood problems, age, and tiredness average across time. On top of that, we have between level variation in the items. For each item, we have a random effect, a random intercept, and it is then measuring the two factors on the between level, F1 and F2, the ones that had a higher correlation than the ones on the within. Note then a couple of details here. On the within level, we call it DSEM because we are looking at the residual relationship between the factors. F1 has a residual relationship to F1 at the previous time point, same for F2. So there's no relationship between F1 for time point t and F1 for time point t minus 1, but it's for the residual. So it becomes a residualized relationship, so hence the R there. Second detail to notice is that this picture is simplified. We don't have the usual connection between the random intercepts, which is for each item, and the observed boxes here, the observed variables up here. That would just make the picture more messy. But it should be understood that these variables, these random intercept, influence the observed variables here. So we have the same latent variable decomposition going also in this picture. It should be understood that it's going on there. So here's how the input looks for step 5a, the picture that we just looked at. So the use variable list then has all of the 6 items, PA low arousal 1 through PA low arousal 3, PA high arousal 1 through 3. And then we have the time invariant covariate and the cycles variables. One cluster variable only because it's 2 level, and the cycles variables are on the within level, as we mentioned. And the between statement then refers to the time invariant covariate. T interval does not change. And here we create an average of tiredness. That's a cluster mean, so we average across the time points and get a cluster mean variable. And we also designate girl as being the dummy variable of interest, x1 and x2 is the same. And then we center the covariates by grand mean centering to simplify the interpretation a tiny bit. Then we have two-level random here. We have to add random because we're going to have random effects. Estimator base, and now we increase the B iterations to do at least 25,000 iterations because these factor models are more complex in terms of the analysis. Turning then to slide 32, we see the factor specification. So on the within level, we defined the factor for PA1, that is the low arousal factor, and for PA2, the high arousal factor. And we do that by freeing all of the loadings and then fixing the factor variances to 1, so setting the metric in the factor variance. And we have a lag1 model, so that's in parentheses &1, referring to the fact that we want to lag this variable, have it be regressed onto itself at an earlier time point, well, at least the residual of it. And if you want to have an equality, you put that in parentheses also. And we're not going to use that in this run. I used that in a cross-classified version. But that's where you would put it. Similarly here then for the high arousal factor, where I put an asterisk for the first one here. It comes in a separate order, so I can't use the list function. I put the most prominent item first as sort of the leading indicator of the factor, just to help with the estimation a little bit. But here comes then the factor regressions onto the cycles coefficients, cycles variables rather, x1 and x2, for the first factor and for the second factor. And we're making those random. So here are the S11 through S22 filled circles in the picture that we looked at. So we regress those factors onto the cycles coefficients, cycles variables rather, and then we take the residual of that as autoregression. So PA1 on that residual on PA1 residual at a time point earlier on. And same thing for PA2 on PA1. And we even have the crossed relationship. So PA1 can be regressed on PA2 and vice versa. So what I'm looking at are these relationships here, these over here, these residual relationships. Then on the between level, you have the between factor 1 and 2, and the same specifications as up here, and no equality across within between, because very often the between loadings are bigger. And I also fixed the variances to 1 here, and I let them be correlated, and I give that a label, which I'm going to discuss in a minute. And I do that because I want to have a way to stabilize the estimation, the algorithm, the Bayesian algorithm, because these are highly correlated factors, 0.83, and that creates a little bit of a difficulty for the estimation. In fact, you could just make this into one single factor, one factor for all 6 items if you wanted to. It wouldn't make much of a difference to the gist of the analysis. And then the key step here, we regress those factors and the random slopes within slopes onto these between level covariates. On slide 33, the input for the 5A run continues with a model prior statement. So that refers to the parameter labeled as C on the previous page. Down here, the factor correlation. We fix the metric in the factor variance to 1, so that's a correlation. And because the factors are highly correlated, we want to help the algorithm, the iterations for finding the estimates, by imposing a mild prior here, an inverse Wishart distribution prior, 0.3. It implies, without going into details, it implies that the prior for this factor correlation is uniform in the range of -1 to +1, so in the range of a correlation. So that helps protecting us from iterations where the factor correlation goes beyond those bounds rather. For instance, going above +1. The rest of the input here concerns the save data statement, and that is a critical one here in step 5a, because we're going to do imputation at the end, as we discussed. This file name using the word imp with an asterisk implies that we're going to have a set of data sets, namely 200 data sets, as we mentioned. 200 data sets are going to be generated with between level components, including the random slopes for the factors on the cycles. Now the regression coefficients on between that you get from slide 32 here, note that they are in the metric of S11 to S22. That is, they are in the metric of the X1, X2 covariates. So they are the beta 1, beta 2 coefficients, random coefficients for each of the two factors. And we discussed the fact that the beta coefficients and their relationship to background covariates is hard to interpret, and that we instead want to make a transformation of those coefficients into amplitude and phase for each of the two factors. So as a first step towards that, we therefore do imputations of 200 data sets here on slide 33. And that's going to move us towards an analysis where amplitude and phase are instead regressed on those covariates. That is, getting to step 5b. So in step 5b, then we start with the data command, file equals fscov imp, and then we add list instead of the asterisk, and we do a type equals imputation analysis. So here we have then an analysis that's repeated for each of the 200 data sets that we created, that we imputed in step 1 and 5a. And the type imputation runs is done for each of the 200 data sets, and we take the average of the estimates and compute the standard errors in line with imputation formulas, as usual in imputation. Now the variable list here then is consisting of only between level variables, the covariates, and the between level factors, and the random coefficients, which also are on between. And we also get factor scores for each of the 6 factors. Now here then in define, we do the transformation from the S variables to amplitude for factor 1 and for factor 2. Down here is a complex statement that really only checks the signs of these random slopes. Here we have 6 cases of combinations of signs for the first factor, and then on the next slide we have it for the second factor. So the signs are positive, positive, negative, positive, etc. And that is described, these are the issues in computing phase. Phase for factor 1 on this slide and phase for factor 2 on the next slide. The intricacies of computing phase is discussed in the appendix in the paper and its supplement. And I'm not going to discuss that here, but it is a critical issue for particularly for Bayesian analysis, to do it in this careful way, taking into account the signs of these random coefficients. But all in all, we're just computing phase for factor 1 and here for factor 2. Now on slide 35 then, we also have some novelties. We have FB iterations as the standard, so fixed number of Bayesian iterations set at 2000, for instance. And we want, that's why, because we want to use the same number of iterations applied to all of the 200 analyses. So that's just a convention we use. So the real issue here then is the model. And here we have then the between factors, the amplitudes for the two factors, the phases for the two factors, regressed on the time invariant covariates. So it's a simple regression model. We have 1, 2, 3, 4, 5, 6 dependent variable regressed on a bunch of covariates. Very simple model. So the analysis is single level. Could be done by ML as well, but we do Bayes here. And then we just tack on a labeling of the coefficients. Here we look at the intercept in that regression, and here then it comes in handy that we did the grand mean centering of the covariates, so the intercepts are the same as the means. And then we can add a little model constraint feature to it, where we look at difference between the factors in amplitude, like we saw that the amplitude was lower for the high arousal factor. We can test if that difference is significant, and same thing for the horizontal shift, the sideways shift in the phase, to see if that's significant. Now some of the results then are as follows, and they're given in more detail in the paper. Turns out that both of the two between level factors are significantly influenced by SDQ, childhood problems, in a negative fashion. So with more childhood problems, you have lower between level factors for positive affect. And you also have a negative relationship from or to the average of the tiredness. That's not the main focus of the analysis. We are really more interested in how the amplitude and phase relate to the covariates. And we find then a difference between the first and the second factor. So for amplitude 1, that is significantly influenced by age in a negative fashion. So the older the kids are, and they vary, I think, in age between 12 and 16. The older they are, the lower the amplitude for the low arousal factor. But there's not a significant difference with respect to age for the high arousal factor, AMP2. So that's a substantive finding that substantive experts can ponder and interpret. Both amplitude 1 and 2 are also positively influenced, significantly so, by the average tiredness. Similarly, there's a difference between the factor in the phase influence. So phase 1 for the low arousal factor is significantly influenced by average tiredness. So that higher tiredness makes for a higher phase, so a later peaking. within the day. For the phase 2, for the high arousal factor, there is no such or no significant influence from any of the covariates.